So the NR is going to be kind of an important one. I would argue, at least in this class, we aren't going to use the NR or no reaction, because when we talk about chemical reactions, I want you to draw out what the products are, even if you think there's no reaction. So the way I visualize a reaction is that it's the plan. It's the plan. If something were to happen, this is what it would be. Okay? How many of you know what you would buy if you won the lottery? Okay, so there's a sizable amount of you that have a plan on what you approximately would do if you won the lottery. Does that mean you've won the lottery? No. The chemical reaction is the plan. Right? It is what could potentially happen if a reaction happened. Right? It's the outline, it's the plan behind it. So I would argue when you go through and do or look at any of the chemical reactions, you should be writing out what the plan is going to be. Right? After you've done that, you could evaluate, does it actually happen? That's where the no reaction could pop up. You will find that some people will go through and be able to predict whether the reaction happens and go, well, A plus B, well, that's not going to happen. That's a no reaction. Right? That is a fine conclusion. It is fine for people to go through and do that. I don't recommend that for the sake of this class. You should be predicting out what you would expect to happen first and foremost, and then you could later answer, well, that's not a reaction. Does that make sense? Right. So that one you could see, not as important. Okay. Really not as important. The heat is a catalyst or the iron is a catalyst. Those aren't that big a deal. And ultimately, that notation is really wishy-washy. Okay. Meaning that notation isn't true for all cases. Okay. Virtually everything up there is true in all cases. Those meanings are valid. Okay? So, in a chemical change, if we go all the way back to people studying chemical changes, Proust came through, or Proust, how would you say his name? I think he's French. Proust. Let's stick with that. Okay? Came up with this law of definite compositions, which meant that compounds will always contain the same elements in a constant proportional mass. Okay, which means if I look at water, whenever I identify water, I will always find that there are 2 grams of water, or hydrogen, for every 16 grams of oxygen. Okay? It doesn't matter where I'm getting the water source from or how I'm testing it, I will always find that that mass ratio holds true. Okay? Well, that doesn't really look like we know what we know about the formula for water, because what's the formula for water? 2 hydrogens, 1 oxygen. Well, Proust, French guy, says it's by mass. Why would he say by mass and not based off of the number of atoms? Does that look like an actual picture? Like, snap, there's a picture. No, what does that look like? A drawing. Why would we have a drawing of this guy? He's that old. Long, long, long dead. Didn't have a concept of what actual atoms were at the time. We didn't have a way to measure atoms. What he had instead was a way to measure mass. Okay, so when he evaluated certain compounds, he noted that we could get different mass amounts of those pieces, but he didn't have a way to break that down into the individual atoms that made it up. Right? And so that's why the atoms are being referenced, or the masses are being referenced, not the atoms, in his eventual theory. This is why Dalton could come along and say, well, actually, there's probably a small particle that's making up that mass, and it's just changing the number of those particles, and you're getting a constant proportion in the number of particles, not based off of mass. Okay, so Proust is mass-based, Dalton is atom-based. That's pretty much it. The thing that I found bizarre, well, how the hell does he measure a mass? How do we measure the mass of hydrogen or oxygen? What's the problem with measuring the mass of hydrogen and oxygen? The atoms themselves are really small. What else makes it difficult to measure the mass of hydrogen and oxygen? Okay, so we could go through and refine that, yeah, Mike screwed up and said these are diatomic, so that should be written H2 and O2. Okay, still isn't going to necessarily mess with the mass, and still doesn't contribute to an issue of why it might be difficult to track those masses. They're gases. Okay? To get a measurable mass of the gas, we have to do a sizable amount of chemistry because the gas is going to take up a very large volume. Okay? So it could be difficult to actually nail down what these masses are, particularly, say, 16 grams of oxygen. Right? That's a relatively large volume of gas to be measuring. Okay? There are ways to go through and do this. Okay? You can take heat, and in this case, potassium perchlorate. If I heat up potassium perchlorate, it decomposes into two separate species, potassium chloride and oxygen. So I could determine the mass of oxygen relative to the mass of potassium and chloride. Okay, so I can come up with ways to actually monitor this that don't involve really fancy equipment. Okay, so in the case of potassium perchlorate, all I really got to do is heat it up. I need a fire, and I need a balance with some sort of precision. Okay, so I don't have to be that fancy. There's other things we can do. You can do electrolysis. You can force electricity into molecules, and that can change their chemistry. We can also run combustion reactions where we trap the varying pieces of the combustion reaction to predict the amounts of, say, carbon, hydrogen, or nitrogen in a particular compound. So there are ways to go through and do this. You don't have to stress about those ways. It's just, it is possible even really early on in chemistry. Okay? Dalton comes through, says mass is not a good idea. We should be going based off of the atoms that go into it. Okay? As a quick kind of reference, if I asked you to build a bicycle, what would you tell me about the number of wheels? Or sorry, let's rephrase that. What would you tell me about the wheels for a bicycle? There's two. You don't tell me it's going to be 1 kilogram of bicycle tires. Okay? The number of them makes a lot more sense than measuring out the mass because we can count that number easier without actually having an instrument to make those measurements. Okay? So Dalton's theory goes into atoms, and that we've already discussed. Right? Which then gets us to our chemical equations. So we saw this chemical equation before. That's when we talked about the diatomic hydrogen. When we're looking at a chemical equation, there's a variety of ways that we could go through and approach this. Okay? And I keep screwing up this example, but I think I finally got a hold of it. If I said took eggs and cheese, what could I make?
Omelet.
I could make an omelet.
Still doesn't look right, but
I think it's 2 T's.
2 T's and an E?
It just does not look right.
there's another E. There's 3 E's.
No.
O-M-E-L-E-T-T.
This is why we have Greg.
And it was Bruce, by the way.
Omelette.
There you go.
Oh.
E?
No, 2 T's still. That's probably French too, but I haven't looked it up.
Yeah, no. According to Google.
Yeah, it's O-M-E-L-E-T.
So if I take some eggs and some cheese, I would make this egg cheese thing. Right? That's it? That explains the full process? What else? Right? We could talk about the cooking of it. True. What else could we consider?
Other ingredients.
I'm keeping it simple, so let's not add other ingredients.
The type of cheese?
We could deal with the type of cheese.
Added to it.
How many eggs? So we could specify the amounts. Okay? For lack of a good descriptor, let's just say 3 eggs and 2 cheese.
Wait.
Don't stress about the units on this.
2 cheese.
What else is going to be important here?
It's state of where it's at.
Okay, so we could reference phases, yeah.
It's a liquid. Oh, that's what you
Yeah, that's our phases. That's not a bad idea. So I just take 3 eggs and 2 cheese, and I put them into a blender and blend them up, and I get my egg cheesy thing, plus cooking. Yeah?
What could we state what we did?
Are there shells on those eggs? Do I really want to put all the shells into my egg cheesy thing? No. So we could add shells out here as an extra kind of byproduct of this. Right? When we're talking about a chemical equation, we need to make sure we account for all of the pieces. When we look at a recipe, we don't account for the waste, okay? Which is actually kind of a big deal when you think about it. When someone goes through to make a product, say like a soda, they go, oh, I've got a soda. I'm going to put it in a can to sell it to people. What are they saying happens to the can?
Ends up in the ocean.
They don't care. And where does the can or the bottle go? Into the garbage. If we're lucky, it makes it into the recycling. But even then, if it makes it to a recycling factory, the recycling factory has to sell that recycled material to somebody else. Does the company want that old leftover stuff? They don't care about it. They want the cleanest, freshest stuff possible. Better for brand imaging. Okay? So we need to be considered or thinking about that entire process. Chemistry at least does a half-decent job in this because it accounts for all of the pieces. We don't just forget that it existed. An egg is composed of the liquidy stuff inside it and that hard outer shell. Okay? We keep the egg stuff for our egg cheesy thing, and we toss the shells as waste. Okay? Our chemical equation needs to account for all of those pieces when we go through and balance this out, or when we go through and process it. Okay? And there should be nothing left over. So when I run this reaction and I take sodium hydride, all of it should react to become somewhere in our products. I don't also get some leftover amount of sodium hydride. Okay? It must all get put into those pieces. Kind of makes sense? Which then means the amounts of each of those pieces needs to be the same on both sides of the equation. Because if it's not the same, I haven't accounted for my waste appropriately, and now I potentially have a problem. Okay? So how do we go through and come up with an accounting procedure for this? What's that? How? How do we balance the equation?
You look at how many there are of each element on both sides and you make sure that they're the same, and if not, then you add.
Okay. We go through and we look for the element, and I agree. Why do we not look for sodium hydride on both sides of the equation?
Because they can be separated.
Because those chemical compounds can break apart and change. Why are we balancing elements and not, say, protons, neutrons, and electrons?
Because we're stating the change in what the compound is, not what the change in charge is.
Okay. We will eventually have to deal with the charge, but why do we typically not look at balancing the protons, neutrons, and electrons?
Because doesn't that tie back into the grams?
I would argue not so much the grams, but the element itself. If I balance the protons from sodium on the left-hand side, how many protons from sodium are going to show up on the right-hand side? The same amount, because the protons define the element. Okay? So as long as the protons, neutrons, and electrons don't change total through the equation, I don't have to worry about them. And what I can do is balance the larger piece. Okay? So I can go through and balance just sodium instead of protons, neutrons, and electrons. Well, how many sodiums are on the left-hand side? One, and on the right-hand side? What about that 2?
It goes for carbon.
Okay. Your subscript values only go to what's directly in front of them. What is directly in front of that 2 is only that carbon. So it doesn't apply to the sodium. So it's 1 and 1. So our sodium is balanced. Now what could we go through and balance? We could attempt to balance the H, and I would argue balancing hydrogen in this case is a horrible idea. Okay? And it's not because it's wrong, it's because... Is it a bad idea to try and solve world peace? No, that's probably a good idea. We should try and do that. Why is it something that we tend to not try and do immediately?
It's such a large task.
It's such a large task. It's difficult. There's a bunch of different little pieces floating around, kind of like hydrogen is floating around in 2 different places on the reactant side and 2 different places on the product side. It could be very easy to lose control of where the hydrogen is, and if it didn't balance out perfectly, I may not be able to easily figure it out. So if an elephant If an only 15 minutes in. This is great. Now I keep trying to say elephant. If an element shows up multiple times on both sides of the equation, don't balance it first. Wait to balance it later and hope and pray that you don't have to worry about the elephant in the room. Right? So what would we balance next?
That's carbon.
Okay, so we've got a suggestion for carbon. Why are you picking carbon?
It's next one.
If we move through our sequence, we said don't balance hydrogen, don't balance hydrogen, the next one would be carbon. Okay? I would actually make the argument that we should not balance carbon either. And I'm not saying you're wrong. There are only two, so why can't we balance it? What is that carbon associated with? This hydrogen and this oxygen. Because that whole thing together is known as acetate. So why can't we just balance that whole piece as acetate? You can. That is exactly what I would argue. We should balance that entire thing as acetate. That way we don't have to break it into carbon, hydrogen, and oxygen. We can just balance it as the acetate species. How many acetates are on the left-hand side? One acetate's on the right. One. So it balances out. Why does this 2 not refer to the acetate? It's referring to the oxygen in the acetate. When I went through to balance the sodium, what did I write? What did I write when I went to balance sodium?
The element and then
I wrote 1. Next thing.
the element symbol.
The element symbol. Could I have balanced sodium by looking for N?
No.
Why not?
It's nitrogen.
That's nitrogen, not sodium. When we go through to balance acetate, that 2 is what makes it acetate. If I make that 2 as how many acetates there are, I'm changing the meaning. That 2 is as much a part of the name or formula for acetate as the A is part of sodium. That's tricky because the number versus the letter mean the same thing, but they're 2 different symbols. Okay? So we have to recognize that our numbers can carry multiple meanings. They can carry meaning towards identifying what our compound is. They can also carry meaning as how many things are present. Okay, so we have to be a little bit careful with those numbers to make sure you nail down exactly what that meaning is. Okay, now what can I balance? The hydrogen. And this is where it's going to get tricky. How many hydrogens on the left? You said 2. Somebody want to challenge that?
5.
Do we include that because it's in the acetate?
Right. I would argue that 2 is absolutely a phenomenal answer for this. When we went through to balance acetate, acetate had H3 in it, which means is that hydrogen needing to be balanced down here? No, it's already been accounted for in the acetate. This becomes tricky because our hydrogen, that symbol for hydrogen now has 2 different meanings. It has the meaning where it was part of acetate, and it has the meaning where it was unbalanced. Right? This is where color coding can come in handy. Have I accounted for this hydrogen? Well, I have now in the 2 hydrogen. That hydrogen. Is this blue set of hydrogens a different set of hydrogen?
Yeah.
Yes. So when I go through and look at the formula, I have to distinguish those differences and acknowledge how I'm going through and balancing it. Does that make sense? Which I then mean go through to the product. How many hydrogens do I have on the product side? Only have the 2 coming in over here. So it's balanced. Because we haven't changed any of those numbers, we don't have to do anything else, and we could just finalize and say we have our answer. Okay? Because you guys have had some practice with this, that sounds pretty good, so you should be able to answer the question, what is the sum of the coefficients on the balanced equation? It's 4. The coefficient is the number in front of each of those species. What is the number in front of each of those species? 1 all the way down the line, and we get a total of 4. Just a...
Yeah.
Okay. What's that?
My leg's falling asleep.
Oh, sorry. I thought I heard... I have a question.
Sorry.
Yeah. Makes sense? Okay. So if that's good, then you should be able to go through and balance your own equations. I would recommend you follow these rules. Okay? The biggest thing that comes out of this is rule 6. You should check your work. Anytime you change a coefficient, you should rebalance the entire equation. Okay, that doesn't mean restart at that point. That means finish balancing out and now restart. Okay? If you change more numbers, restart the whole process again. Okay? Or recycle the whole process. The reason being is that that allows you to check your work and verify what's going on behind it. Right? So that if you do this right, this should be fantastic. Balancing equations, you should be able to walk out of the exam going, I got every single question right. Or,
I got everything wrong.
I got every single question wrong. There is no middle ground with balancing equations, sort of. There's one little tiny exception. We won't stress too much on that. Okay? But when it comes to balancing equations, you are either 100% right or you are 100% wrong. There is no middle ground. That's why you check your work. The checking the work sets that up so that you are guaranteed to be right. Okay? How many times you should check your work? My general recommendation is you should check it as often as it takes for you to get just slightly irritated at me. Okay? That I am making you check your work that much. That builds a little bit of emotion. We tie emotions to memories. There we go. You'll now permanently remember it, and I don't have to talk about it again. Don't get so irritated with me that you're going to spite me and get it wrong. Okay? Just enough irritation that you're going to remember it. Make sense? Okay. Your turn. Okay. I was told that second one was on the quiz, but I don't think I worked through it. Did I work through the second one? On the play posit? I don't, yeah. Okay, I think you had to solve the second one. Okay, so go through and attempt to solve it, and then we'll go through and solve that one together. The first one and the third, you'll find if you go through and do those, should be trivial, okay, because they're all not already balanced, but they should be really easy to balance. If you want a little warm up into doing the second one, that's fine. Okay, start with the first one. Okay? Otherwise, jump straight to the second one, see what you can do to come up with unbalancing that. Okay, so we're going to go through and look at this one, and we're going to attempt to balance it in a couple different fashions. Okay, and it's going to get a bit messy because of the couple different fashions we're trying. Okay, so if we go through and start, we need to balance each of the pieces on each side of the equation. What's the first piece we want to attempt to balance?
Aluminum.
Okay, aluminum's a good place to start. Why'd you guys pick aluminum? It's the first thing when we read left to right. That's cool. How many aluminums do I have on the left? 2. Okay? That's what that symbol means. If I broke down what this thing looks like, we have 2 aluminums. We have SO4, 3. So what does this mean? I have 1, 2, 3 SO4s. SO4 happens to have what charge? It's a -2. For those of you trying to think through and be like, I hope I don't have to remember that. You do. That is one I told you need to memorize. So sulfate, we have 3 sulfates, those are circles, all with a -2. So each of them have a -1. When we go through and look at the aluminum, there's 2 aluminums. What's the charge on aluminum? +3. Plus, 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 plus. Okay? How do we know this was the correct formula? Well, the charges must cancel. Plus cancels with a minus. Plus cancels with a minus. So if I only had 1 of each, I'd have an overall +1 charge. That doesn't work. So I needed another sulfate to cancel out that positive. But now I have an excess of negative, right? Yeah, we're going to have to make that a little bit bigger. Sorry. On my screen, it looks fine. Is that a little better? Okay. When we go through and just had one of each, a positive cancels a negative, a positive cancels a negative. If the formula was just AlSO4, the overall charge would be positive. Okay? Because when I put together a compound, the charge must cancel, I'd have to throw in another sulfate to cancel that. But by throwing in another sulfate, I now have an excess of a -1. So I have to cancel that by throwing in another aluminum. But now I have two positives, so I throw in another sulfate to cancel that charge. The overall result is how many aluminums do I have? I have 2 aluminums. How many sulfates do I have? That's where that formula comes from. So when I break down that formula, it allows me to see the individual component pieces that go into it. You'll notice that when I broke this down, I said 2 aluminums and 2 sulfates. I didn't mention how many sulfurs and oxygens. Why not?
Because they're together.
They are together. Sulfate is one complex ion that fits together. The complex ions are effectively a new element for you to go through and memorize. And as long as they don't change through the equation, I can keep them grouped together as a single unit. All right? If we go through and now look at the product side of this with just the aluminums, I can't do just the aluminums. I need a different color though. So our aluminum, positive, 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 and our nitrate, make it orange, is just 1, -1. Okay? If we try to cancel the charge, positive cancels one of those negatives. I still have too much positive, so what happens?
2 more.
I need 2 more negatives so that the charges all cancel out. The total is I have 1 aluminum and I have 3 nitrates. That's where that formula is coming from. That's the meaning behind those. So that subscript 3 outside the parentheses is referencing how many of those nitrates I have. What does the subscript 3 within the parentheses mean?
You have 3 oxygens.
Okay, one option is to go through and say, I have 3 oxygens. Okay, that answer is not wrong, but I would take a step back from that. Because if that's the explanation, then why did I not draw out all 3 oxygens?
It's just considered nitrogen.
Okay, I would argue that 3 is what makes that nitrate. Okay? When we go through to balance aluminum, what if I went through and said, well, actually, I'm going to balance A and L? What element is element A? There isn't one. Okay? I can't drop the L from that being aluminum. Because if I drop the L from it, I change the meaning of that statement. Okay? Just like that subscript 3 within the nitrate, that purple 3, that 3 makes that nitrate. If I drop that 3 or change that 3, it's no longer that species, and now all of my balancing rules change. Okay? This is tricky because the purple 3 goes to the meaning of the name, and the orange 3 goes to the meaning of the amount of that thing that's present. Okay? For instance, let's see if I can pull this off. What did I just write? How did you know that was chem? Because that's CH3M. How did you know that was chem?
Well, if you've ever seen any Eminem albums.
Okay. Eminem albums, that's fine. I'm okay with that. What if I'd gone through and spelled... Oh gosh, that was a horrible way to do it. Cat. How'd you know that was cat?
Because that's supposed to be an at symbol.
That's supposed to be an at symbol. And when you spell cat, you spell cat with an at symbol?
Yep, no, but you know.
No, but you know. There's a translation feature happening there. That symbol you're translating into a different meaning. When we go through and look at the purple 3, that purple 3 may look like an at symbol, but we know that that 3 is referencing the identity of that compound. Whereas that 3, the orange 3, is now referencing the amount. Depending on the context of where that symbol is located, it changes the meaning behind it. Okay? That is a challenging concept to deal with because that symbol is showing up ultimately in the same type of location, but it holds different meaning. So you have to separate that. Okay? And you have to recognize that information, and that is challenging to deal with.
But we learned all about writing systems, so you know to look for context clues and strange symbols in strange places with different.
Yes.
Yeah.
Okay? So how many aluminums show up on the left-hand side of the equation?
2.
Okay? We have that subscript 2 meaning that. I also drew it out nice and neatly above. How many aluminums do I have? 2. How many aluminums do I have on the right-hand side of the equation? 1. We know it's 1 because the subscript next to the aluminum is? There isn't something there. By definition, that's going to mean 1. I could also look at the drawing. There's 1 there. Is the aluminum balanced? No. I need the aluminum to balance. How do I ensure that it balances? Okay. I need at least 2 aluminums. So I would have to have another aluminum here. But for me to include another aluminum, I have to reference where it's coming from. Where is the aluminum on the right-hand side coming from? Is there just aluminum chilling by itself on the right-hand side of the equation? Yes? Where does it say just aluminum? Nowhere. It's contextualized in the presence of nitrate, which means for that aluminum to show up, what also has to show up? How many nitrates? 3 nitrates. Why do I know there has to be 3 nitrates? To balance out the aluminum, I need to have those 3 nitrates. Okay? Now that allows me to put a 2 here. I'm changing the coefficient in front. Okay? If I had just drawn in, I may regret this. I don't think I'll regret this. If I had just done that, then what I'm doing is changing the meaning, whoops, maybe I will regret this, changing the meaning of the formula by changing that 2 in there. I can't do that. When I'm going to balance the equation, the meaning of the formula must stay the same. Okay? When I go to make cookies and I have too many chocolate chips, that doesn't mean all of a sudden I get to make brownies. You started making cookies. Keep making them freaking cookies. Don't switch it up.
You can never have too many chocolate chips.
Well,
That's a...
We don't need to go that far, but yes. Right? What happens with the next thing? What's the next thing I would attempt to balance? Right? I could try and go through and balance the nitrate, and I would argue I should not be balancing nitrate first.
BA.
Why BA?
Because it's all by its nonsense.
Right? I would argue we should not balance even the BA. Why should we balance the sulfate next?
Because it's right after...
Reading left to right, what's the next thing we encounter after aluminum? Sulfate. The formula for sulfate is SO4. This is where things can get tricky again because we have that 4, and I'm attempting to color code and failing miserably at it. We have that 4 in there, which could be confusing. This is where I've actually saw a couple people come up with a neat little cheat on this. I don't want to balance SO4, I want to balance sulfate. How many sulfates on the left-hand side of the equation? 3. That's what these red circles were. Those were all sulfates. What is the formula for sulfate? SO4. It is that parenthetical. It is that 3 that is applying to the parentheses. Kind of, sort of? How many on the right-hand side of the equation? 1. This is where people will jump and go, well, there's 4. Just because we got rid of the parenthetical doesn't mean it's not really there. Sulfate is SO4. How many SO4s are present? Only one. Okay, if we were to go through and draw that one out, there's our sulfate with a -2 charge. Our barium, what color do I have now? I need to do purple. Barium is what charge? A +2. So if I looked at that formula, the plus cancels the minus, the plus cancels the minus. There's one of each of those. Okay, so I have one sulfate on the right-hand side of the equation. I have 3 sulfates on the left. Does it balance?
Nope.
So what do I need to do? I need to make sure I have 3 sulfates. How do I get 3 sulfates? Does the sulfate just show up on its own? No, what is the sulfate tied to? Barium. So to bring in a new sulfate, what do I have to do? Bring in a new barium. I have another sulfate. I have to bring in a new barium. How many of those do I have? 3. The 3, what color am I? I'm red now. Is the coefficient in front. I have 3 of those repeating units. Seeing it? All right, now what could I balance? Now I could do the barium. Notice I will write it as Ba, and that's what I'm balancing. I'm not going to attempt to balance B. Why not? B is boron. Same kind of ideas happening with the sulfate, except now it's a little bit clearer because they're all letters. We don't have numbers also referencing names. Here it's all letters. How many bariums do I have on the left? Okay, 1. Again, that could be difficult to see, so we could write it out. There's our barium. What color do I have for nitrate? Orange. Nitrate is what charge? Nitrate is a -1. Yes, that is one you are required to memorize. If we tried to balance that formula, one of each doesn't work. Okay? I would need another nitrate to balance that out. Okay? So nitrates on the left, barium's on the left. Just 1. Barium's on the right. 3. Is it balanced? How do I fix it? I would need to add 2 more bariums in, but remember, every time I bring in a barium, I also bring in 2 nitrates. How many total bariums do I now have on the left-hand side? 3. There's my total. Okay? Nitrates. Now I'll go through as NO3. How many on the left? 2 places to look. We could say, oh, there's only 2. No, because I had that 3 in the front. So I just add them up and I get 5. Remember, we drew it out. How many nitrates do I have? There's 6 spheres. Okay? We drew them in that way to help with that visualization. You have to deal with the multiplier across that. We get 6 nitrates on the left. How many nitrates on the right? 6. Also get 6. Is the nitrate balanced? Yes. Because we changed numbers, what should we do? Check the work by deleting it all and restarting. Okay, and by deleting it all I mean is the work down here at the bottom. I'm not about to draw all those freaking circles again. Okay, aluminum's on the left. 2. We can see that as the subscript 2 there. I can also see it as there being 2 aluminums. On the right, 2. Let's be weird. Barium. 3 and I heard a 6. Why are you saying a 6?
Sorry, I didn't mean that.
It's okay.
I was just going too fast, but I know that the 2 belongs to the nitrate, so that's not.
The 2 only applies to what's directly in front of it, which is the parenthetical. Barium's not in that parenthetical. It's a common mistake. That's why I wanted you to say it. That was good. Okay? So we have to watch out for that referencing. Okay? On the right-hand side, 3. Nitrates. On the right-hand side.
6.
And on the left, 6. Sulfate, 3 and 3. Because I didn't change any numbers, everything's now balanced. Okay? When we're looking at our chemical formula, What we're representing is everything directly above it. Okay? That black box represents a single formula unit for this. Oh, I missed that one. Everybody kind of seeing the patterns? Oh, man, F nuggets. Because that's a big complex one. Okay? So when we talk about balancing formulas, coming up with how to do nomenclature, I don't care that you name the compound. I do care that you understand how to balance out those charges. Why is that important? How do you balance an equation? It's the exact same freaking process. If you don't know how to come up with the name of a compound, the process behind it, you can't come up with a chemical equation. You'll fail at balancing that too. The exact names isn't important. What is important is processing out those pieces.
Just so when I solved it, I first went to each element and then found how many, and went down and then went backward to the top to balance. Do you think that's a bad habit or?
So one cycle I've seen students do is start with aluminum and then do barium, then do nitrate, then do sulfate, and just write the numbers down as they go. Okay? Well, if we looked at the old work, when we did aluminum, I changed the numbers, right? Which then meant those numbers changed, which means when I went through and did it, wrote all the numbers down, the very next thing I'm going to do is change all of the numbers. So I'm going to do all of this work, then immediately go back and change some of it, and then do all of the work and go, oh crap, I got to change some more of it. And you're going to end up doing such an iterative process back and forth that you're repeating a bunch of work that you never had to repeat. If you balance it immediately as you move through, you don't have to repeat that cycle.
For the beginning, does it matter if we put a 1 there or not?
So, the big question that could come out of this would be, what would I ask on a test? That's a lot of work shown up there. Right? Just walking around, some people got to the answer without showing any of that work because they could do all of that stuff in their brain. That's cool, that's awesome, that's fantastic for them. Okay? If I make them do all this, are they going to get upset? Yes. Okay? That's not nice, so I'm not going to do that. So when it comes to balancing questions, those questions are multiple choice. If you can internalize it and do it in your head, by all means go ahead and do it. I don't recommend it because you increase the odds of making a mistake. You should write it down. The suggested work would be down at the bottom, not the stuff up at the top. Right? That's what you should be showing so that you know and you track. Okay? When it comes to what question I could ask on a multiple choice test, what is the coefficient in front of barium nitrate in the balanced equation? 3. Okay? I would also include the number 2 and 1. Okay? 1, because if we're just like, oh, it's just balanced, it's just a number in front, we could put it there. I could even put on 0 just to see what you were thinking there. Okay? I could also ask, what is the coefficient in front of aluminum sulfate in the balanced equation? It's 1. So to your question, should you include the number 1 in front of aluminum sulfate? Is it helpful for you to know that there's a 1 there? Yeah? Then you should include it. Is it a requirement? No. Because it is an implied number, just like when we look at barium nitrate, we don't specify that subscript 1 for the barium. Right? That's a slightly different case because if you do specify the subscript for the barium there, you're technically wrong. That's nomenclature for you. There isn't an IUPAC for balancing equations where you have to or don't have to specify it. Okay? But to ensure you minimize mistakes, always putting a coefficient there is not a bad idea.
And keep in mind that when you're showing your work, that is a writing consideration. It's to help you store things somewhere other than your brain. And I'm someone who can do a lot of math in my head fairly easily. It's the reason I was really good at inventory control. But there comes a point when you're developing a skill or a pattern for more complex problems. Like right now, the first balancing equation you guys did that was just, what was it, hydrogen and...
Hydrogen bromine
Yeah,
to make
like
hydrogen bromine.
that you probably could have done in your head. But when you're dealing with more complex things like this, or more complex reactions where you're dealing with charge and coefficients and all these, that's a lot of information to store in your brain, and you have other writing technologies to store that information. So yeah, that's just my writing take on it.
Kind of makes sense? Okay. It requires practice, just like nomenclature. So you need to be doing that practice. Okay. What we will be seeing probably in a couple slides here, because I want it earlier on, is conversions. Conversions are also going to require practice to get used to that process. We've got a bunch of stuff that needs to be practiced for the next exam, next Thursday. Okay? So it's coming up very, very fast. You should be doing lots and lots of practice. If you haven't been, you got a week. 2 to 3 hours minimum per day practicing. Okay? The next thing I would argue doesn't really require practice, it's classifying chemical reactions. Okay, so this is less practice and just exposure to looking at different chemical reactions to come up with ways to classify them. These are your major categories. There's actually a sixth one. That sixth one is a combustion reaction. You're also responsible for that. Okay. This equation is not shown as balanced. The x and the y say it doesn't really matter what x and y are, there are just some numbers there. But you're starting with some carbon and hydrogen compound, you react it with oxygen, and it produces water and CO2. Okay? When we look at these categories, some of these categories are going to become more important than others. Okay? Pretty much, actually, these categories are going to be the most important or extra important for you. Why are those going to be extra important? Yeah, I will test you on, but I'm going to test you on the combination and decomposition too. But it's a different level. You're responsible for identifying each of these 6 reactions. I show you a reaction, you should be able to look at it and be like, that's a combination. That's a single replacement. Those bottom 4 become extra difficult because not only do you have to be able to predict that it is a particular type, but what has now been changed? What changed to the slide? What happened to the product? It's gone. Guess what you're responsible for with those bottom 4 reactions? Predicting what the products are. Okay? So now, not only do you have to be able to identify each of these categories, you have to be able to look at just the reactants of a single replacement and be like, those are going to be the products. I know that's going to be the answer. Okay? Once you have the chemical equation, what could you then be asked to do with it? You could be asked to balance it. So all of these things stack on top of each other. Okay? A weakness at any one of these points causes the whole system to shatter. This is why you need that practice to build up to it. Okay? Because conversions is important enough to me, we're actually going to skip this slide for the moment. We'll come back to it Thursday. And I want to set up the converting process so that you can start also working on practicing this. Okay? This is something in this unit that tends to get people irritated because they know how to do a conversion. Okay? If I give you, come on now, 36 inches, and I want to know how many feet that is. 3 feet. How'd you do that? 36 divided by 12. 36 divided by 12 is what? 3. Does anybody see feet? So I'm going to say your explanation is wrong. 36 divided by 12 is a phenomenal answer for solving for 3. That says nothing about the conversion.
There's 12 inches in a foot. So.
Okay, there's 12 inches in a foot. So how does that get incorporated into this?
So you write 12 inches equals 1 foot to begin with.
Okay, so we could go through and say 12 inches equals 1 foot.
Yeah, and then you can write 36 inches divided by 12 inches.
Did I give you 36 inches per 12 inches?
No, but you're trying to figure out how many feet it was.
Didn't ask that. Did I give you 36 inches is 12 inches?
Can you use a cross multiple?
Did I give you 36 inches is 12 inches?
No.
No, I said 36 inches. By you writing 36 inches divided by 12 inches, I know what you're trying to do, okay? That's a separate issue. You're now saying that that information was given. That was a given value. Is that true? No. So you should not be writing 36 inches divided by 12 inches. This is a formatting issue. And this is why people get irritated with me. That's okay. This is part of that helping you remember it. Okay? I gave you 36 inches. 36 inches per what?
Equals 3 feet, right?
No.
I did not tell you 3 feet. You told me 3 feet. 36 inches divided by what? 1. If it was anything other than 1, it wouldn't be 36 inches.
So can we cross multiply from that?
Okay? So one option is to go through and say cross multiply. Cross multiply works great if we said 36 inches is how many feet equals 12 inches in 1 foot. Okay? And yes, now you could go through and do this cross multiply thing. Okay? Which is fantastic. That works great for how many conversions? 1. What if I give you 5 conversions? That process is going to suck. Right? In fact, it's probably going to suck so badly it's going to fail, and you'll get the answer wrong. Okay? Remember, we talked about some meaning, so I really liked where you went with saying 12 inches equals 1 foot. That was a phenomenal place to start. And I gave you some really important information when we talked about our conversions. This was the mathematics, and we said we could convert this into useful mathematics because I can turn that into 1. Why do I want to turn it into 1? What's anything multiplied by 1? It's the same thing. Okay? So that works. So let's convert this into 1. Okay? Which 1 do I want? Do I want 12 inches over 1 foot equaling 1? Or do I want 1 foot over 12 inches equals 1? Why do I want 1 foot over 12 inches equals 1?
Cancel the label.
Because if I now insert that conversion factor as a new piece of given information, what happens? What happens to the units? The units cancel. And now what happens? 36 times 1 in the numerator. What's in the denominator? 1 times 12, which gets me 36 divided by 12. What happens with my units? Hallelujah, I'm left with feet. That is a proper system for work. We're not integrating different conversion factors or different pieces of information. We keep each unit of information independent from every other unit of information, and we don't try and jam multiple things in at the same time. Okay? All you got to do is try and leave the room to see evidence for why that's important. You're like, that's kind of dumb. How is leaving the room? Everybody leave the room at the exact same instant. How is that going to work?
Like Friday.
Okay? It's probably not going to work very well. Why not? You can't fit. Remember how we talked about memory stuff? Your brain can only hold so much stuff. Don't cram multiple pieces together. Keep them as independent units. That will allow you to manipulate them a little bit smoother and easier. Okay? And allow you to see mistakes in your work and your lineup. What we just walked through is a process known as dimensional analysis, also known as the unit factor of those things down there. Okay? That process, the textbook has actually done a pretty good job of outlining. It really comes down to 3 steps. Step number 1, know where you're going. Right? Which may seem really simple to write down an equals and what unit you want for the end. Okay? Why are you taking this class? For a degree. Right? If you came into this class having no clue why you were taking the class, how valuable is the class going to be? Okay? Probably not at all. If you know you need it for a degree, does that provide you a little bit of incentive to actually learn the material? At very least, learn it well enough to get a grade. Okay? If you have no reason for doing something, what are the odds of you doing it? How many of you have a reason to clean my house? Damn it. Okay? None of you are going to do it. Okay? Unless there was some other incentive behind it. And I'm not offering extra credit for that because then you would know where I live. Okay? Brings in all sorts of other weird things. Okay? So we want to know our goal. Where are we going? Once we know where we want to go, we have to know what information we have coming into this. Are we prepared for it? To take this class, you have to have certain prerequisites established. Okay? You had to know that information before you started the process. Then you get into the class, and now that's the unit factor. That's step 3. That's dealing with Mike throughout the semester, or Greg, depending on which class we want to talk about. Okay? Now you have to deal with each of those new pieces of information and fit them in with the given context you already have. Okay? Well, what if you don't fit them in with the given context? Are you going to end up at your goal? Who knows? Maybe, maybe not. Okay? So this process works pretty darn well as an analogy for our everyday life and what we're trying to do. When you get in the car and start the engine of the car, do you know where you're going? I would hope so. You watch the road, maybe people don't. Okay? There's a goal in mind. You have to know that goal before you start. Then you start including each new piece of information. Okay? That is that process. The whole point of this, and this is where it gets kind of a bit nitpicky on this, is every example we're going to go through and do is probably something you've done already and have something in your mind of how you want to do it. How did you convert inches to feet? What did you do? What did you suggest, James? What did you do? You didn't just say 36 inches was 3 feet. How did you get to the feet?
12 inches in a foot and then multiplied it by 3.
You divided by 12. That's what you told me to do. Okay? You had an algorithm for it. You've done these conversions a whole bunch of times. You've created a system that allowed you to not think about what you were doing so that you could solve it faster. The whole point of this section on conversions is not to verify that you know how to do those conversions. I really don't care. You probably already did. The whole point of this unit is to verify that this process that I'm telling you to do works for you. Okay? Because what's going to happen in the next unit is I'm going to give you things that you don't have any concept for, you don't have any algorithm for, which means will you be able to solve them using your algorithm? No. If you don't have a process to fall back on, what happens? You fail miserably at it, and I really don't want that. So when you go through and do any of the conversions, this is in chapter 2, right? Your focus on this is not getting an answer. Your focus is what is the process that you went through to get that answer, and does that process match what Mike told me to do? Does it match what the textbook told me to do? That's my goal in this unit. Okay? I really don't care so much that you're doing the conversion. Right? I care about your process. Does it kind of make sense? Okay. We are unfortunately out of time. We'll do a couple examples with the converting process on Thursday, and then we'll go back to looking at those chemical equations and being able to process that information, and then we'll kind of see where we go from there. We're going to be jumping all over the place, I think.